Okay, so today we'll be covering approximating heat correlation, so figuring out what like parameters such as H, the coefficient of heat transfer, what those could be in different geometries, because we don't always know what exactly they can be in a problem in the wild, and so we need to find a way in order to approximate them. So the first thing to do is usually identify what the geometry is, right? So identify geometry. So sometimes you'll see things like maybe it's a flow through a pipe, maybe it's a flow through a plate, right? So in this scenario, we have the plate right here, right? We have this plate, and we have, if I was to draw, a certain boundary at which the fluid was to start flowing, it would look something like this. We would have the velocity of the fluid going like this, and then slowly decreasing, right? And the reason for this is we have the no slip boundary condition over here, where the velocity of the fluid must equal basically the velocity of the material over the plate or the surface. And so you see this velocity profile, but we need to find a way, a certain way to describe this behavior that we can give an overall h, because the velocity is changing, and we want to know, okay, how much heat transfer is this fluid taking with it. And so usually when you have some things like this, you'll have this like boundary. So this boundary that you call a film. And so what we want to do is basically discover, okay, what is the temperature of that film, and then use that in order to calculate other parameters that will allow us to finally find H. And so let's get started on that. So the first thing to do is to basically define T film. Actually, first identify the geometry. So in this case, we have a plate, right? And the second thing to do is to basically find T film, the temperature of the film. Find T film. All right. So what is T film? T film is basically the average of the temperature of the surface plus the bulk temperature. So I'll show you what that would look like. So I have an example over here where if we go over here, you'll see that this is also a plate, right? But we have the temperature of the surface. So this could be some sort of bar, like a copper bar that we're throwing water on. And the temperature of the surface would be the temperature of the copper. And then the bulk temperature would be the temperature of the air, let's say, right? And so we have this system, and we want to average these two in order to figure out what the film temperature is. All right, so we basically average the two, and then the third thing that we do now that we have that, is let's choose a different color. Um, the third thing that we do is we calculate the Reynolds number and the Prandtl number at that temperature, at T film. So Reynolds number, right? Some of you might know the Reynolds number is basically a dimensionless parameter that describes the flow, the flow of the fluid. So a high Reynolds number is usually a turbulent flow, versus a low Reynolds number is a laminar flow. And so the way how we calculate the Reynolds number is uh, the density of the fluid times the velocity of the fluid times the length, right, of which it's going over, divided by the dynamic viscosity. Sometimes you'll also see it written as um, the velocity of the fluid times the length divided by something called kinematic viscosity. Sorry, which the kinematic viscosity is essentially just uh, the viscosity, the dynamic viscosity divided by the density. So this is the equivalent things. And it's important to know that these are not the same at every single temperature, which is why we're looking at calculating these at a particular temperature. The density, as you might expect, can change. The water's density, for example, at maybe 5 degrees Celsius is not the same thing as water's density at 98. So these parameters can change, and so it's really important that we calculate what the Reynolds number is, so that we can know, okay, is this a laminar flow or is this a turbulent flow? Turbulent flow, as you might imagine, can carry heat really well compared to laminar flow. And so we really want to know what kind of flow is going on in order to use the right correlation. All right, so now we can go on to the Prandtl number. So the Prandtl number here, let me write what they are. So this is Reynolds, and this is Prandtl. All right, and the Prandtl number is equivalent to mu, which is remember, it's the viscosity, the specific heat, divided by the conductivity. And so if you want to intuit what the Prandtl number means, is it's basically comparing, okay, well, how well does the fluid dissipate momentum versus how well it dissipates the heat. So it's momentum diffusivity divided by thermal diffusivity. And so we need this to know, okay, well, how much heat is the fluid going to carry away? And so these parameters, very similar to the Reynolds number, they change depending on the temperature. So especially specific heat, that changes at different temperatures, and so it's important to calculate this. Um, okay, perfect. So now that we have those down, the next thing that we do, right? The next thing that we can do is to use the appropriate correlation for the geometry of the flow. So use appropriate correlation for flow geometry. Well, what does this mean, right? Well, as I was saying before, the flow geometry plays a large role in figuring out, okay, well, what kind of H are we going to be calculating? If it's a pipe, it's different versus if it was a flat plate. And I have this this graphic over here, this image that displays that, right? So this is just generally what the correlations look like. This is for a plate, but essentially you calculate the Nusselt number. So I'll tell you what the Nusselt number is. The Nusselt number, that is basically equivalent to the heat transfer coefficient times the length divided by K fluid. And what it's basically describing is, it describes, okay, well, what kind of resistance am I getting from conduction versus convective resistance? We're comparing the two. And that's what the Nusselt number is. And this is the way how we're going to get the H for this geometry. But in order to get the Nusselt number is basically going to be found as some sort of relation between the Reynolds number and the Prandtl number. So if I go back to this graphic, right, you can see that, okay, well, we have these different constants in front of them, but these exponents can change too depending on the geometry. So if it was to be a pipe, these exponents would change, and they're not particularly nice looking. These are okay, right? These are a half and a third, but sometimes it can be 1/12 and other, like, not non nice numbers. And so it's really important to figure out what the correlation is in order to figure out what the Nusselt number is. And so I'll write an example of what a Nusselt number could be. It could be, right, we'll take this one. So if I was to, let's take this and we'll go ahead and transplant it down here. Oop, that is quite large. And so this is an example of what it could look like. All right, so once we've calculated the Nusselt number, right, we basically just solve for H. And so it's pretty simple. Um, the next thing to do, go back. Um, the next thing to do, right, is to solve for H. So H, yeah, judging from this equation, if we were to solve for it, it would equal the Nusselt number times the conductivity of the fluid divided by L. And this will essentially give you the overall, not the overall, but the fluid's convective coefficient for heat transfer. And that's all you need to know.